Welcome back, ladies and gentlemen, to AP Chemistry with Mr. Kenton. Glad you guys could join me today. We are continuing our discussion through Unit 3 by looking at now solutions and all things that have to do with solutions within the context of chemistry. And so, just as a quick reminder here, that the topics that we're going to be covering, we're going to focus on solutions and mixtures, representations of solutions, and solubility. And this information can be found in Chapter 13 in the Brown and LeMay textbook. It's going to correspond to sections 1 through 5. And I'm not going to read off this list of problems to you, but you do have problems from Chapter 13 that you can complete as we are going through and taking these notes. So we just finished up talking about gases, and we're transitioning here into solutions and mixtures. And it's going to make a pretty nice segue here. So as we transition into looking at solutions, just want to take some time to ground ourselves and remind ourselves of some things that should be prior knowledge. And here are some diagrams I would imagine that you're relatively familiar with as it pertains to looking at different phases of matter. Obviously, we've been dealing with gases here recently, and then when we were dealing with intermolecular forces, we talked a lot about solids and liquids. And these representations go along with the kinetic theory of matter. And so we see that gases very disorderly, a lot of empty space, particles have a lot of freedom to move. Liquids, there's a little bit of disorder. You've got particles or clusters that are free to move over each other. And then within your solids, there's an orderly arrangement. And these are probably representations that you've seen probably since middle school science. And as you can see, that as you add or remove heat, that's what allows us to change between our different phases of matter. Now, that's also going to lead us to classification of matter, which again should be something that we're familiar with. That's a flow chart that comes from the textbook, and it gives you just a series of questions to think about when it comes to classifying matter. Now, remember, a pure substance can be broken down into two different categories, if you will. The first one being elements. And when you think about an element, these are things that are found directly on the periodic table. And when you start to look at them from a particle perspective, there's only one type of atom that's going to be present at the atomic scale. Right? You also have compounds. These are another category within pure substances. And compounds are substances that are made from two or more different kinds of atoms. And they're also going to follow the law of constant composition, which essentially says that when you're dealing with a compound, no matter what once you have a compound like water, for example, water is always going to be H2O. It's always going to be chemically bonded in that ratio for the substance to be water. And again, it's a pure substance because it has two or more different kinds of atoms, but they've been chemically connected. They can't be physically separated. Now, it's important to recognize that within your pure substances, we could classify elements and compounds as homogeneous, right? They have all the same type of atoms, so they look the same. They're uniform throughout. Now, the other classification we can think about is going to be with mixtures, right? And remember, mixtures are going to be physical combinations of two or more pure substances. Now, your mixtures can be broken down into different categories as well. Homogeneous or homogeneous mixtures are going to be the same throughout. And important characteristic is that they're going to have identical properties everywhere in the mixture, right? So the particles are going to be evenly distributed throughout, and the physical properties of the mixture are going to be everywhere in the mixture. And this type of mixture is also commonly referred to as a solution, which is what we're going to be spending the bulk of our time here looking at as we end Unit 3. Now, the other type of mixture that we need to be aware of are heterogeneous mixtures. And heterogeneous mixtures can be described or defined as mixtures of pure substances where you've got 2 or 3 different phases of matter. So you might have liquids and solids, or maybe liquids and gases, or maybe solids and liquids, or solids and gases that are interacting, but they are visibly different. It doesn't look uniform. We can visibly distinguish the different pure substances that are making up that particular mixture. Okay. All right. Now, having that as a backdrop will lead us into the solution process and how solutions actually form. And so, just as a reminder, a solution is a homogeneous mixture, right? Those terms are interchangeable. And to form a solution, you have to have a solute, something that's present in a relatively small amount, that is dissolved or placed in a solvent, which is present in a larger amount. So your solute is typically the thing that is being dissolved, and the solvent is typically the thing that's doing the dissolving. And the second thing I want us to consider as we're looking at the solution process is that when you're making solutions with condensed phases, what that means is when you're dealing with solids and liquids that are making your solution, that what happens is that in the process of that solution being formed, that the intermolecular forces between the solid and the liquid are being rearranged to allow the solution to form. Okay. Excuse me. So those are some things to keep in the back of our mind as we look at the solution process, and certainly intermolecular forces are going to be a topic that we're going to be revisiting throughout this particular topic. Now, here are some examples of some solutions. And the thing that I want you guys to take away from this particular image, this table that can be found in your textbook, is that solutions can be in either the solid, liquid, or gas state, right? And what you should note is that the state of the solvent is what's going to determine the state of the solution. And what I like here is there are lots of different examples of the different types. So you've got air as an example of a solution, oxygen and water as an example, alcohol and water, salt and water, hydrogen and palladium, mercury and silver, silver and gold. So you're getting to see all these different types of solutions that are possible. Now, for us, I want us to consider one where we have sodium chloride as our solute, and we've got water as our solvent. So there we've got a crystalline structure of sodium chloride. And so here we're going to have, since water is our solvent, we're going to have a solution that's going to take place in the liquid phase. Now, when sodium chloride dissolves in water, we're going to take a look at what's going on at the atomic level. And so in AP, you guys should be getting more and more familiar, more and more comfortable with particle level representations. It's going to certainly be something that you might see on an AP exam. And so what you can see here from these images is if we start in the topmost image, that's when the green and purple spheres represent sodium chloride, and you can see that you've got the red and white balls. Those represent the water molecules. And so this is at the initial phase at which the solution is being formed. So at this point, the sodium chloride is being surrounded by water. And as this happens, the water molecules are going to begin to form ion-dipole interactions with the sodium chloride salt, right? And as you can see, the water molecules are going in and they're orienting themselves so that the polar ends of the molecules match up so that new interactions can be formed. And so we can see here that water is surrounding the chlorine, and we see that water is surrounding the sodium ion. Well, in the solution process, this is going to continue until all of the ions have been completely surrounded by the water molecules. And if you guys recall from honors chemistry, that process was referred to as solvation, S-O-L-V-A-T-I-O-N. And when we were dealing with water as a solvent, that's going to be referred to as hydration, and that's just the process at which a solute is being completely surrounded by its solvent. Now, if we take a even closer look, if we look at it at just an individual basis, right, you notice we've got our water molecules, our sodium ion, and our chloride ion. And so from what you guys should gather from when we talked about intermolecular forces, notice that the water molecules have oriented themselves in such a way that the negative end of the water molecule is orienting itself towards sodium ion so that ion-dipole forces can be formed. And then with the chloride ion, the positive ends of the water molecule near the hydrogens are forming ion-dipole interactions with the chloride ion. And so that's just an idea, and you can see that the water molecules have completely surrounded the ions on all sides, right? And so that would be an example of the solvation and hydration process, just looking at it at an individual particle level. Now, understanding that that's what's going on, looking at it from the particles, but there's an energy component that we're going to take a look at and examine here within the solution process as well. And so you should see listed over here to the right, there's an image, and it's got delta H1, which is going to be the separation of the solute molecules. So that's going to be the breaking of the intermolecular forces in the solute. You've got delta H2, so the energy required to separate the solvent molecules. Again, you're adding in energy breaking the intermolecular forces within your solvent. And then you've got delta H3, which is the formation of the solute-solvent interaction. So when the newly separated solute and solvent interact, they go into those spaces that have been created, and they form new intermolecular forces of attraction. So that's kind of the summary of that energy process. Now let me kind of put that into words as well. So there are energy changes that are taking place when a solution is being formed. You know, we've listed that here. And when we talk about solution formation, there are always going to be 3 energy steps in the formation of a solution. You're going to have the separation of the solute molecules, which we're going to refer to as delta H1. You're going to have the separation of the solvent molecules, which we're going to refer to as delta H2. Now, it's important to recognize that when we talk about the separation of solute and solvent, those are going to be steps that require energy, so they're going to be endothermic. So energy is going to have to go into the solute and the solvent for those changes to take place. And then the third step is going to be the formation of solute-solvent interaction. So that's delta H3. Now, when we're forming these interactions, that's when energy is going to be released. So delta H3 would be an exothermic step. And just to summarize from those, delta H1 and delta H2 will always be endothermic, so they'll always have a positive energy value. And delta H3 is always going to be exothermic, so it's always going to be releasing energy, and so its delta H value is always going to be negative. Now, as we begin to look at this, enthalpy is a fancy word that chemists use to describe changes in energy. We're going to look at enthalpy a lot more in Unit 5. But for now, just understand that enthalpy is dealing with energy changes, specifically heat. Changing in the solution process, it's going to be as follows. So the enthalpy of a solution, delta H SOLN, is going to be equal to the sum of delta H1, delta H2, and delta H3. It's that straightforward. If you know those particular values, you can figure out the energy change or the enthalpy change for a given solution process. Now, when delta H of the solution is positive, that means that the solution formation is going to be endothermic. If delta H of solution is negative, that means it's exothermic. And delta H of solution is going to depend entirely on the intermolecular forces between our solute, our solvent, and then the newly formed interactions that take place when the solution forms. So just keep that in mind. And as I mentioned earlier, breaking attractive intermolecular forces is always endothermic, so that's delta H1 and delta H2. And then forming attractive intermolecular forces is always exothermic. So delta H3 will always be exothermic. It'll always have a negative value associated with it. Okay. Now, here is another way to represent the solution formation process. And as you're looking at this, you should notice that both diagrams are showing the solution process, but the one on the left is showing us a process that's exothermic. And we see that it's exothermic because the solvent and solute are higher in energy than the solution itself when it gets formed. And so we see that there's a net release of energy here, so that would make it exothermic, right? On the right, we see that the solution itself is higher in energy than the solvent and solute, and so therefore it's going to require energy to make the solution, right? And again, we can follow along. All of the purple arrows are showing steps that require energy to be input into the system, right? So delta H1 and delta H2, and both of those are purple. Energy is being put into the system. And then you've got the red arrows, delta H3, in both of them in this case, because energy is being released. That's exothermic. And then for our exothermic process, we've got a delta H solution that's going to be negative, right? And so again, it's just a different way to think about the process of what's going on when a solution is being formed. And so to determine whether delta H solution is positive or negative, we're going to consider the strength of all of the solute-solute and solute-solvent interactions that are taking place. And so in our cases, what's either going to happen is delta H3 is going to be greater than the sum of delta H1 or delta H2 and delta H2, or delta H3 is going to be less than the sum of delta H1 and delta H2. And so that will determine whether or not it's endothermic or exothermic. All right, last thing that I want us to take a look at as it pertains to the solution process is another component that we're only going to introduce very briefly here. And it's the idea of what's called spontaneity and disorder. Okay, so there's an energy component that's based off of, is it energetically favorable for a solution to form? But there's another factor that's going to determine whether or not a solution is going to form as well. And so we think of solutions, a spontaneous process occurs without outside intervention. And so if you look at the image at the bottom of the screen, you've got two liquids that are separated by a divider, and one's blue and one's pink. And so a spontaneous process would be something that occurs without outside intervention. So what would happen if we remove that divider, then what's going to happen is the blue and pink liquids are going to mix, and they're going to form that purple solution that we see that's in the final phase in that beaker, right? And so it's not like when we remove the divider that the blue and the pink liquids are just going to stay separated. It's easier for them to begin to interact, and as they interact, that's when you start to see that color change. And so spontaneous processes generally lead to a greater state of disorder, right? So they become less organized, right? The beaker on the left is more organized, the beaker on the right is less organized. Now, when the energy of the system decreases, we'd say the process is spontaneous. And so when energy is being released by a system, that tends to be a spontaneous process. Now, interestingly enough, some spontaneous processes do not involve the system moving to a lower energy state. For an example, an endothermic reaction, something like the formation, like making an instant ice pack. What happens is you've got two solutions that are mixing together, but energy is having to actually go into them in order for the process to take place. And yet, once they mix, this process continues, and it has to deal with the fact that the amount of disorder that has been created as a result of that is what's increasing that. So that's going to conclude our first video as it approaches and looks at solutions. And we've looked at it from the perspective of the different types of solutions, whether they could be solids, liquids, or gases. We've looked at what's going on at the particle level of the solvation and hydration process. We've also looked at it from an energy perspective, at looking at the enthalpies associated with the solute, the solvent, and then the new solute-solvent interactions. We've also looked at it from the perspective of spontaneity and disorder in this particular video. Thank you guys for joining me. Appreciate you guys taking the opportunity to watch this. Please make sure you complete the Google form after you watch this video and let us know what your questions are. Thank you guys so much, and we'll see you again soon.